Small sample hypothesis tests. Example 3a. In a sample of n equal 3 patients, the proportion cured by new drug, p hat, 2 out of 3 or 0.67, is known that the proportion cured by the old drug, p is equal to 0.6, and the proportion not cured, bq, is 1 minus p, or 1 minus 0.6 is 0.4. We want to test the following hypotheses at the alpha equal 0.05 level of significance. H0, p is equal to 0.6, new drug is not better than the old, versus H1, p is greater than 0.6, new drug is better than the old. So we first want to check to see whether n times p is greater than or equal to 5, or n times q is greater than or equal to 5. If so, then we can use the z-table as a shortcut. If not, we'll have to use the exact binomial probabilities. So our sample size n is 3, and p, if h0 is true, p is going to be 0.6, so the proportion cured is going to be 0.6. 3 times 0.6 is 1.8, greater than or equal to 5, and that's a no. 1.8, not bigger than 5. We can also check whether n times q is at least 5, and 3 times 0.4 is 1.2, greater than or equal to 5, and that's a no. So we need both of these to be yeses, actually. If it's yes, no, no, yes, no, no, then we'll have to use the exact binomial probabilities. And some books have a different standard. We're going to be using 5 as our standard here, the cutoff point, but the bigger these numbers are, the closer the z-table will come to the exact probabilities. Some texts use the number 10. They want n times p to be at least 10 and n times q to be at least 10. But we'll usually use 5. Okay, so we can't use the z-table. We'll have to use the exact binomial probabilities. It's called binomial because they have 2 possible outcomes for each case. Either the patient is cured or not cured, and it's a random variable because the number of patients cured can vary from one sample to another. And we're going to use a tree diagram. There's several ways of computing binomial probabilities, but we're going to use a tree diagram, and we'll set up the tree diagram as if H0 was true, and so as if each patient has a 60% chance of being cured and a 40% chance of not being cured. Okay, so let's set up the tree diagram. Okay, so the first patient is either cured or not. And if H0 is true, they have a 0.6 chance of being cured, 0.4 chance of not being cured. So that's the first patient. The second patient is also either cured or not. Okay. I'm going to abbreviate this C and N, cured and not. So the probability of cured is 0.6, probability not cured is 0.4. Okay, so that's the second patient. So every time you add a patient, the number of paths to the tree doubles. So we have, with one patient, we only have 2 possibilities. Either the patient is cured or not. But with 2 patients, now we have 4 possible outcomes. They could both be cured. That's cured. First patient is cured, the second patient not cured. First patient not cured, the second patient cured, or they're both not cured. So there's 4 possible paths to the tree. And then the third patient is also either cured or not. And if H0 is true, they have a 0.6 chance of being cured, 0.4 chance of not being cured. So that's the third patient. So now there's 8 possible outcomes. Okay. We can multiply straight across to get the probability of each path. Try to get a little more space here. I'm running out of room. Okay, so the top path, all 3 patients are cured. So that's, we'll put that in red. So it's 0.6 times 0.6 times 0.6. So we want to multiply 0.6 times 0.6 times 0.6 is 0.216. And that's all 3 are cured. Okay, the second path, we're going to have 0.6 times 0.6 times 0.4. So that's going to be 0.6 times 0.6 at 0.4, 0.144. 0.6 times 0.6 is 0.36, and then times 4 is 0.144. So that's cured, not. The next path, cured, not, and cured. So it's 0.6 times 0.4 times 0.6. So that's will also be 0.144. So that's cured, not, and then cured. And then we have next path we can skip because our sample proportion was 2 out of 3. So we really only need the paths where at least 2 out of 3 were cured. So this path here we have cured, not. So there's we can skip that path because we only really need the paths where at least 2 of the 3 were cured. Next path we have not, cured, 0.4 times 0.6 times 0.6, 0.144. That's going to be not, cured. And the rest of these paths we can skip. We have next path here we have not cured, then cured, and then not. We can skip that path. Not, and cured, and not, and not. So we can skip the paths where we have less than 2 cured. So then we can to get the p-value. We can add up these numbers here, the 0.216 plus 0.144 plus 0.144 plus 0.144. So 6 and 4 is 10, 14, 18. Carry the 1. 1, 2, 6, 10, 14. Carry the 1. 1, 2, 3, 4, 5, 6. So the total is going to be 0.648. So our p-value is 0.648. Okay. So it's the probability of getting 2 out of 3 cured if H0 is true. Some in my lab on some of the questions will ask you to put this information in a table. So we can put, there's 4 paths where at least 2 of the 3 were cured. So we can put those that information into a table. Sometimes it's more convenient to do it that way. So we have the cured, all 3 were cured. So that's going to be 0.6 times 0.6 times 0.6, which would be at 0.216. And the probability of the first 2 are cured, the third one's not. 0.6 times 0.6 times 0.4, 0.144. And then we have the first and third are cured, the second one is not cured, so we have 0.6 times 0.4 times 0.6, 0.144. and then the first patient is not cured, the last two are cured. That's going to be 0.4 times 0.6 times 0.6, 0.144, and then the total will give the p-value of 0.648. Okay, so this p-value is more than our desired level of doubt, which is 0.05. So the p-value of 0.648 is greater than alpha, which is 0.05. And it might help to add an extra 0 so we have the same number of digits. It makes it easier to compare. So 648 is more than 50. So that means we fail to reject H0. Sample does not provide enough evidence to say the new drug is better than the old drug. Technically, we never accept H0. Either we reject H0 or we don't know. Sample does not provide enough evidence to say the new drug is better than the old. The sample proportion is a little bit more than the proportion cured by the old drug. We have a proportion of 0.67. It's a little bit more than our the old drug, which cured 0.6. So it looks like it could be a little bit better, but the evidence is not strong enough. It could have been it might have happened just by chance that in this sample we had a slightly higher cure rate than the old drug, and that's partly because of the small sample size too. With the small samples, usually are not going to give you enough evidence to reject H0. Okay, so as a comment, researchers might use a higher or lower value of alpha, for example 0.1 or 0.01, depending on how cautious they want to be about rejecting the null hypothesis. Other researchers simply report a p-value without specifying alpha. Generally, the lower the p-value, the stronger the conclusion. And the chart below gives us some guidance in interpreting p-values. And so our p-values had 3 decimal digits, so it might help to add some trailing zeros here so that it makes it easier to compare the numbers, so that we have 3 digits behind all of these. Okay, so anyway, the our p-value of 0.648 is more than 0.1. So this provides little evidence. The adjective here is little. Okay. So the p-value of 0.648 is between 0.100 and 1, so the sample provides little evidence. Little evidence that the new drug is better. The new drug is better than the old. Okay, so you can also make a diagram showing the possible outcomes of hypothesis testing. Either H0 is true or H1 is true, and either we don't reject H naught. Or we reject H naught. Okay. So there'll be 4 possible outcomes. Okay, so if we reject H naught and H naught is true, that's called a type 1 error. And the probability, that's determined by the researchers. The researcher determines how cautious they want to be about making a type 1 error, and that's alpha, and often it's going to be 0.05 or 0.01. We'll usually use 0.05. And then the confidence level, it would be 1 minus alpha. If we don't reject H naught and H1 is true, that's called a type 2 error. And we use the Greek letter beta, it looks like a B, to represent the probability of a type 2 error, and then 1 minus beta is what's called the power. So 1 minus alpha is our desired level of confidence. Alpha is a Greek letter representing the level of significance. I like to call it the level of doubt. P-value, here it says actual level of doubt, but more precisely it's the probability of rejecting H naught if H naught is true. And we like that to be small. Beta, Greek letter beta, probability of a type 2 error. 1 minus beta is called the power of the test. And because we failed to reject H naught, what type of error might we be making? I'll give you a minute to think about it. Okay, so whenever we fail to reject H naught, we take a chance of making a type 2 error. Okay, so this would be a type 2 error. If you reject H naught, you take a chance of making a type 1 error. If you don't reject H naught, you take a chance of making a type 2 error. Okay, so let's redo example 3a. If the proportion cured by a new drug, p hat, is 1 out of 3. So we can use the same tree as we had before. Each patient is either cured or not. And we make the tree as if H naught was true. I'm going to C is cured. I'm trying to fit this in the space, so we're going to write out the word cured here. So they have a 0.6 chance of being cured, 0.4 chance of not being cured. So that's the first patient. And the second patient is also either cured or not. And the probability of 0.6, 0.4, 0.6, 0.4, second patient. Third patient is also either cured or not. And the probabilities are 0.6, 0.4, 0.6, 0.4, 0.6, 0.4, 0.6, 0.4. Okay, so if 1 out of 3, we need to include all the paths where at least one patient is cured. So actually we're going to include all paths except the bottom path where none of the patients were cured. So we can skip the bottom path, but all the other patients, all the other paths will be included. We want to include all the paths where at least one were cured. So top path, all 3 were cured. Cured, cured, cured. And we want to multiply 0.6 times 0.6 times 0.6. That'd be 0.216. And then cured, cured, not. So So that'll be 0.6 times 0.6 times 0.4, 0.144. Cured, not cured. It's going to be 0.6 times 0.4 times 0.6, 0.144. Cured, not not. So that'll be 0.6 times 0.4 times 0.4. So that'd be 0.096. Cured, not not. Somehow I lost my meeting here. Okay. So that's going to be 0.096. And then we have next path, not cured, cured, 0.144. Not cured, not. It's 0.4 times 0.6 times 0.4. It'll be 0.096. And then we have not cured. 0.4 times 0.4 times 0.6, 0.096. So we want to get the total here to get the p-value. So 6 and 4 is 10, 20, 36, carry the 3. 3 and 1 is 4, 8, 12, 21, 25, 34, 43. Carry the 4. 4 and 2 is 6, 7, 8, 9. 0.936. So our p-value in this case is even higher. So it provides even weaker evidence that the new drug is better than the old. The p-value of 0.936 is greater than alpha, which is 0.05. So sample does not provide enough evidence. That's even weaker evidence that the new drug is better. Okay. Okay, so example 3C. Let's redo example 3A if the proportion cured by the new drug p hat is 3 out of 3. So we can use the same tree, but now we want all the paths where at least 3 of the 3 were cured, and that's actually going to only be one path. So the first patient is either cured or not. 0.6, 0.4. And then the second patient also either cured or not, but now we have 4 possible outcomes. 0.6, 0.4, 0.6, 0.4. And the third patient also either cured or not. That's the third patient. Probability 0.6, 0.4, 0.6, 0.4, 0.6, 0.4, 0.6, 0.4. So there's only one path where all 3 were cured. So that, well, multiply 0.6 times 0.6 times 0.6, 0.216. And the rest of the paths we can skip. So we want to skip these where less than 3 were cured. So the p-value, there's only one number to add there. The p-value is going to be 0.216. So that evidence is a little bit stronger, but still weak evidence because of our small sample size. The p-value of 0.216 is less than alpha, which is 0.05, and so we again failed to reject H naught. Sample does not provide enough evidence. You say the new drug is better. And that concludes this presentation.